to the user. So the user basically has to verify without seeing 50K. So this is simple query. And we also consider more expressive queries. For example, nested query. You want to compute an average first for a certain group of people and then compute a max. So this kind of nested query will be quite commonly used in database systems, and how to verify the correctness and the completeness for those queries. And also for selection, we want to also consider multi-attribute selections. Not only just one attribute, but multi-attributes. All right, so here will be some basic building blocks that we used. And this is a commitment scheme. Commitment scheme is very commonly used, for example, in contract signing, optimistic exchange. It has two operations. So one is commit, the other is open. The data owner has a value X. At the beginning, the data owner does not want to. So the X is secret to the data owner. So the data owner will compute a commitment of X. And this usually makes use of a random value, R. The commitment is given to the user. The user may do some operation based on the commitment. And later on, the data owner can open the commitment by revealing X and R. The user can compare whether the previous commitment is correctly computed based on X and R. So if you think of an analogy of this, so basically without open, a commitment is useless because the user cannot verify it is correct or not. So analogy of this is sort of, if you think of commitment is like an engagement and the open is like a wedding. So without the wedding, the engagement is kind of useless. And you have to have both parts of it in the system in order to verify certain number is correctly computed. And what we use is two properties of a commitment. One is hiding, the other is binding. Hiding is once you see a commitment, you cannot guess the value that is committed. Once you see C, you cannot guess X. And the binding means a commitment can only be opened to one value. So this is a commitment scheme. And we actually use the Patterson commitment scheme, which is a specific kind of commitment scheme. It has this nice property of a linear homomorphism. Essentially, it means commitments, the product of two commitments equal to the commitment of the sum. So it's highlighted in the green formula. So essentially, a user can compute a commitment of something without even knowing what it is. And the rest of it is just some details. We will not cover it here. Now, here we have a quite complex data structure that we use to bookkeeping the values, the commitments, and the indexes. And here I'm going to tell you the data structure in the most general form. And then later on, when I dive into the detailed examples, we'll actually use a very simple data structure. But here, if you consider a database table that only have two attributes, the data owner will maintain a database table that has actually 4 extra columns. The middle ones are commitments of each individual values. Okay, and the last 2 columns are indexes. Indexes representing the sorting of the each data entries, and their indexes in the sorted list are kept. So you can see the age is sorted already, so the index is 1, 2, 3, 4. Now, the database owner will construct a Merkle hash tree just as before, but this Merkle hash tree will have a lot more contents. For each row, the plain text value, commitments, and the index are hashed together. And this is done for each row, and the root hash is computed. So the indexes, so the last two columns are used here for us to prove the completeness property of a certain query. So essentially, it will be clear later on, but you can think about if the data is sorted based on certain attributes, and then you can prove to the user that the elements that are out of the range is greater than the selected component or lower than the selected component. So you can use a sorted list to prove the completeness quite easily. And those indexes are used for that. Now the root hash is again signed by the data owner, and this information, all the entries in the table and the signature given to the service provider. Okay. So I'll talk about how to do sum verification and also how to do max. And for those, for example, average and count, it is based on sum. So once you know how to do sum, you can do those. And the min and max can be done in a similar fashion. So the basic idea is the database owner commit to each individual data entries and then sign the root hash of the commitments. And the user will obtain a query results and also use the commitments and the signature to verify the correctness of the query. Now again, we're going to use the homomorphic property of a commitment scheme, which will be clear in a minute. So consider a very simple database that has one attribute, 4 data record. The data owner will make the commitments and assign the hash of the commitments, give all these information to the middleman. Now the user query for the sum of all the data record. The service provider will compute the sum using the plain text data, and then give the sum, the commitment, the signature, and the random value R to the user. The random value R is used to open the commitment of the sum. So what the user do is go through this 3-step verification algorithm. First is to compute the commitment of the sum. Notice that using homomorphism property, the user doesn't have to know each individual value in order to get the commitment of the sum. It will just compute the product of all the commitments. And then verify the commitment is truly corresponding bind to the sum by using R to open it. So the user knows 265, knows R, and open the commitment. And then finally, the user will verify the signature for all the commitments. And the signature is used to authenticate the commitments, because without the signature, anyone can compute the commitments, and the user will not be able to tell whether it's a commitment of the original value or something completely made up. All right. So this is a sum verification. Now, for the max verification, we'll have to use an additional building block, which is called the zero-knowledge proof of a greater than relation. So the purpose is to prove two numbers are, one number is greater than the other without actually revealing both of them. So for example, you have a prover that has two numbers, 5 and 10. The verifier